Our universe is hiding secrets that could shatter our reality. We are on the verge of rewriting the textbooks of physics, astronomy, and even biology, all because of 30 astonishing discoveries made in the depths of space. By the end of this journey, you will see the cosmos through entirely new eyes. We will confront a strange object that sailed between stars, a gas on Venus that hints at life, and a cosmic force so baffling it threatens our entire model of the universe. Each finding is a piece of a puzzle, pulling us closer to answers we have not even known how to ask. Are you ready to question everything you thought was true? The first piece of evidence arrived without warning in the autumn of 2017. A telescope in Hawaii spotted a faint point of light moving at impossible speed, a trajectory so extreme it could have only one origin. This object was not from our solar system. It was the first confirmed visitor from the vast ocean between stars, and we named it Oumuamua, a Hawaiian term for scout from the distant past. Its arrival was a monumental first, but its behavior was what truly ignited the mystery. As it hurtled away from the sun, something bizarre happened. It sped up. Gravity alone could not explain this extra push. Comets often accelerate like this when their icy surfaces heat up and vent gas, creating a natural rocket effect. Yet Oumuamua showed no visible coma, no tail of dust and gas that telescopes could detect. It was a dark, silent, and strangely elongated object, tumbling through space like a cosmic cigar. The lack of outgassing meant the acceleration had no clear source, sparking intense debate. Was it a comet after all, with hidden vents of exotic ice? Could it be a porous asteroid pushed by the subtle pressure of sunlight itself? Or was it something our textbooks had never prepared us for? Its very shape defied expectation. Most natural objects in space are lumpy, but Oumuamua appeared to be highly elongated, perhaps 10 times longer than it was wide. This odd form challenged our basic models of how objects form, whether around our sun or another. The discovery ripped open a new chapter in astronomy, proving that interstellar traffic is real and that the building blocks of other star systems are now passing through our cosmic neighborhood. It forced us to build new tools, new watch programs, because if one scout has arrived, countless more are surely on the way. While Oumuamua offered a mystery from the void, the next discovery struck far closer to home, within the swirling clouds of our own planetary neighbor. In 2020, a team of astronomers made a startling announcement. They had detected the spectral signature of phosphine gas high in the temperate cloud decks of Venus. On its own, this might sound like a minor chemical footnote, but the context is everything. On Earth, phosphine is a molecule that screams life. It is produced in significant quantities by anaerobic bacteria thriving in places like swamps, marshes, and even animal intestines. While trace amounts can be forged by extreme volcanic or lightning processes, the sheer quantity suggested by the Venus data pointed toward something far more extraordinary. Here was a potential biosignature, a chemical hint of biology, floating in the surprisingly balmy upper atmosphere of a world long written off as a hellscape. The clouds of Venus, about 30 miles up, enjoy Earth-like pressures and temperatures. It is a stark contrast to the surface below, which is hot enough to melt lead and crushed under an atmosphere 90 times thicker than our own. Could this temperate aerial zone be a refuge, a niche where microbial life akin to extremophiles on Earth might float and survive? The implications were staggering. We would not need to look across light years to find another abode for life. It might be hanging in the skies next door, yet science thrives on skepticism, and this finding ignited a firestorm of debate. Other teams reanalyzed the data, questioning the processing methods and suggesting the signal might actually be from ordinary sulfur dioxide, a common volcanic gas on Venus. Subsequent observations failed to consistently confirm the phosphine detection, casting a shadow of doubt over the initial euphoria. but the idea, once seeded, is incredibly difficult to uproot. The possibility of aerial microbial life on Venus remains a tantalizing, paradigm-shifting mystery. It forces us to reconsider what a habitable zone truly means. Life may not need a gentle, rocky planet with liquid water on its surface. It might find a way in the most unexpected places, drifting in the acidic clouds of our closest planetary twin, forever changing how we see our place in the cosmos. The search for cosmic life often focuses on chemistry, but the universe also speaks in bursts of raw energy. Far beyond our solar system, in the deep darkness between galaxies, something is firing off unimaginably powerful signals. These are fast radio bursts, or FRB. For a few thousandths of a second, a source out there releases more energy than our sun does in 80 years, all concentrated into a single blast of radio waves. When astronomers first detected these fleeting pulses, the leading theory was a catastrophic one-time event, the final, violent death cry of a star collapsing into a black hole or a collision between incredibly dense objects like neutron stars. These were cosmic fireworks, brilliant and then gone forever. That was until we found one that repeated. The discovery of the first repeating FRB source was a paradigm shift. It meant the engine behind these bursts was not destroyed in the process. Whatever was creating these titanic flashes was doing it again and again and again, surviving the unimaginable forces involved. This single fact ruled out a whole class of one-time cataclysms and forced scientists to consider persistent cosmic power plants. The prime suspect now is a type of stellar corpse called a magnetar, a neutron star with a magnetic field so intense it could strip the information from a credit card halfway across the solar system. Theorists suggest that starquakes on the surface of a magnetar, or sudden rearrangements of its monstrous magnetic field, could crackle with the energy needed to produce these bursts. Yet other, more exotic ideas remain on the table, including the inevitable, thrilling speculation about advanced civilizations. Could these be pulses from interstellar beacons, or even leakage from unimaginably powerful light sails propelling ships between stars? While this is the least likely explanation, it underscores just how extraordinary these signals are. Beyond their mysterious origin, FRBs have a practical, revolutionary use. As these radio waves race across billions of light years, they pass through the diffuse gas and plasma that floats in the vast voids between galaxies. This material is nearly invisible to our telescopes, yet it makes up a significant portion of the universe's so-called missing matter. Each FRB is like a cosmic flashlight. By measuring how the burst's different frequencies are slowed and scattered by this invisible material, astronomers can use it to literally weigh the universe. Every new FRB detection adds another data point, helping us build a three-dimensional map of the unseen scaffolding upon which galaxies are built. So these mysterious signals are not just cosmic puzzles, they are becoming essential tools, turning the deepest darkness of space into a canvas we are just beginning to measure. The universe holds its water in the strangest of places. For decades, we believed the moon was a bone-dry desert, its surface scoured clean by the unfiltered vacuum of space and the sun's relentless radiation. Any water, we thought, could only survive as ancient ice buried in the permanent, frigid shadows at the lunar poles, places where sunlight has not touched for billions of years. That assumption was shattered when a flying observatory, a modified Boeing 747 jet named SOFIA, turned its gaze toward a sun-bathed lunar crater called Clavius. High in Earth's atmosphere, above most of our own water vapor, its infrared telescope detected the unmistakable signature of water molecules, not just hints of hydrogen, which could be from other sources, but the chemical fingerprint of H2O, clinging to the lunar soil in a region fully exposed to daylight. This was not a vast ocean or even a puddle, but water nonetheless, trapped within glass beads formed by micrometeorite impacts or nestled between grains of regolith. The discovery rewrote the rules. How could water survive there? The moon has no atmosphere to speak of, and daytime temperatures soar well past the boiling point of water. Scientists believe the answer lies in the unique, porous nature of the lunar surface. The water molecules might be so well sheltered within tiny shadows cast by soil particles that the sun's energy cannot reach them to boil them away. Or they could be loosely bound to the minerals themselves, only released when heated. This changes everything for the future of lunar exploration. Water is the gold of spaceflight. It is heavy and prohibitively expensive to launch from Earth, but if we can extract it from the moon itself, it becomes a transformative resource. With enough of it, we could split it into hydrogen and oxygen, the most powerful chemical rocket propellant combination that exists. A lunar outpost could, in essence, mine ice from the shadowed poles and harvest trace water from sunlit soil to create a depot, a cosmic gas station for missions venturing deeper into the solar system. It also means water for drinking, for growing plants, and for creating breathable air for astronauts. The moon is no longer just a destination. It is potentially the first stepping stone and supply depot for humanity's journey to Mars and beyond, all because we found water where we least expected it. That search for a cosmic whisper once found a candidate so shocking it was literally circled and labeled with a single exclamatory word. In August of 1977, a radio telescope in Ohio, part of the Search for Extraterrestrial Intelligence program, recorded a 72-second burst of radio waves so extraordinary that the volunteer astronomer reviewing the data printout scribbled "wow" next to the signal's alphanumeric code. It was a strong, narrowband signal, precisely the kind an artificial transmitter would produce, and it appeared to originate from the direction of the constellation Sagittarius. Crucially, it matched the expected frequency of the hydrogen line, a quiet channel in the radio spectrum that many scientists had theorized would be a logical calling card for a civilization trying to announce its presence. The WOW signal was never heard again, despite dozens of follow-up attempts over the decades. It remains the most famous, tantalizing, and frustrating non-detection in the history of SETI. Modern reanalyzers have tried to pin it down, with one recent study suggesting it could have been a comet that was not in catalogs at the time, though this explanation remains hotly contested. The signal's enduring power is not in an answer, but in the profound question it etched into our collective consciousness. For one brief moment, the universe seemed to speak directly to us. That solitary event set a standard, and today's searches are far more sophisticated, sifting through cosmic noise with algorithms that can process millions of signals per second. Projects like Breakthrough scan the sky with unprecedented sensitivity, and they too have found their own enigmatic whispers. One candidate, named BLC-1, came from the direction of our closest stellar neighbor, Proxima Centauri. It was a narrowband signal that appeared only when the telescope was pointed at that star, and it drifted in frequency in a way consistent with a transmitter located on a planet. The excitement was palpable, but the scientific process is rigorous. After months of analysis, the most likely explanation turned out to be human-made radio interference, a form of technological mimicry that fooled even advanced filters. This outcome, while disappointing, is a vital part of the search. Each false alarm teaches us how to better distinguish Earth's cacophony from a genuine signal from the stars. These modern candidates, even the unconfirmed ones, are what keep the search alive. They are reminders that the great silence we perceive may simply be because we have not yet learned to listen in the right way or for long enough. Every unexplained blip, every tantalizing maybe, refines the hunt and fuels the enduring hope that one day the signal will not fade. It will repeat, and it will change everything we know about our lonely place in the cosmos. The search for a signal from the stars is a quest for connection, but sometimes the universe presents us with an entire neighborhood of possibilities at once. In a quiet corner of the constellation Aquarius, a small, dim star named TRAPPIST-1 is doing something extraordinary. Orbiting this ultra-cool dwarf, a star barely larger than Jupiter and far cooler than our Sun, are not one, not two, but 7 rocky worlds, each roughly the size of Earth. It is a miniature solar system, a cosmic Swiss watch with all its gears turning in incredibly tight formation. The entire system would fit comfortably inside the orbit of Mercury in our own solar system, meaning these planets are very close to their star and to each other. From the surface of one, you might see the neighboring worlds hanging in the sky, not as mere points of light, but as visible orbs showing distinct features, a breathtaking celestial panorama. The most thrilling detail, however, is their location. Several of these 7 sisters orbit within the star's habitable zone, that theoretical band where temperatures are just right for liquid water to exist on a planet's surface. Given their Earth-like size and composition, the possibility is electrifying. Could these worlds hold vast oceans or at least pockets of life-sustaining water? The compact nature of the system creates a unique laboratory. Because the planets orbit so closely, they transit or pass in front of their star very frequently from our vantage point. Every time a planet transits, a tiny fraction of the star's light filters through its atmosphere if it has one. Scientists can dissect that starlight, looking for the chemical fingerprints of gases like oxygen, methane, or carbon dioxide. This is where the James Webb Space Telescope becomes our greatest tool. Its powerful infrared eye is perfectly suited to analyze the atmospheres of these distant worlds. With each observation, Webb is searching for biosignatures, the telltale signs that these planets are not just rocky spheres but living, breathing worlds. The very existence of the TRAPPIST-1 system forces us to expand our imagination. Our own solar system, with its wide, spacious orbits, might be the exception rather than the rule. Life may not require a bright sun like ours or planets spaced far apart. It could thrive in the gentle, perpetual twilight of a cool red star on worlds that are cosmic next-door neighbors, their fates intimately intertwined by gravity. This crowded, compact family of planets presents our best and closest chance to answer the ancient question of whether we are alone, not by listening for a signal, but by literally sniffing the air of another world. The search for life on distant worlds asks what is possible, but some discoveries in the cosmos seem to defy what should be possible entirely. Recent observations from the James Webb Space Telescope have revealed a population of cosmic monsters that simply should not exist. These are supermassive black holes, the gravitational hearts of ancient galaxies, seen when the universe was less than 500 million years old. According to our best models of cosmic evolution, that is not enough time for them to grow. Yet there they are, already weighing billions of times the mass of our Sun. One of the most startling examples is the black hole at the core of a galaxy called GNZ11. This object is observed as the universe was a mere 400 million years old, a cosmic toddler by universal standards. Yet the energy pouring from its core suggests it is already a behemoth, feasting on matter at a ferocious rate. How do you build a billion solar mass black hole in what amounts to a cosmic blink of an eye? The standard story no longer fits. We thought these giants grew slowly, starting from the collapsed core of a massive first-generation star, a seed perhaps 100 times the Sun's mass. That seed would then gradually pull in gas and merge with other black holes over billions of years. The new Webb data shows there was no gradual phase. These black holes were born big, or they grew at a pace that shatters all known limits, a process scientists call super-Eddington accretion, where matter falls in so violently it defies the normal rules that should push material away. This discovery forces a profound rewrite of our cosmic origin story. It suggests that the first black holes might not have come from stars at all. Instead, they could have formed directly from the collapse of immense clouds of primordial gas in the universe's dark ages, leaping into existence as ready-made giants. Or it implies that the relationship between a galaxy and its central black hole is far more intimate and rapid than we ever guessed, with each fueling the other's growth in a frenzied dance of creation. These impossible monsters are not just ancient relics, they are urgent clues. They tell us that the infancy of the universe was a time of extreme and violent physics, a period where the rules we take for granted today might have been wildly different. Unraveling their origin is now one of the most pressing puzzles in all of cosmology, because to understand these impossible giants is to understand how the universe built its very first structures, setting the stage for everything that followed, including us. This growing tension in our cosmic models is not confined to the ancient past. It is tearing at the very fabric of our present understanding of the universe itself. Astronomers are now facing a fundamental crisis, a disagreement so severe it has been dubbed the Hubble tension. At its heart is a simple, profound question: how fast is the universe expanding right now? We have two supremely confident, yet completely contradictory, ways to find the answer. The first method looks back to the universe's infancy, to the afterglow of the Big Bang known as the cosmic microwave background. By mapping the subtle imperfections in this ancient light, we can extrapolate the universe's entire expansion history and calculate what the expansion rate should be today. This method, championed by the Planck satellite, gives us a very precise number. The second method measures the expansion directly in our modern cosmic neighborhood. We observe the distances and velocities of nearby supernova and pulsating stars called Cepheids, building a cosmic ladder step by step. This approach, refined over decades by teams using the Hubble Space Telescope, gives us a different, equally precise number. The problem is, these two numbers do not match. The local measurements suggest the universe is expanding significantly faster than the pristine early universe implies it should be. This is not a small statistical fluke. It is a persistent, glaring discrepancy that has survived years of reanalysis and improved observations. It means one of our foundational assumptions about the cosmos is wrong. Our standard model of cosmology, known as lambda CDM, which elegantly describes a universe dominated by dark energy and cold dark matter, might have a critical flaw. Perhaps dark energy is not a constant force as we have assumed, but something that evolves and grows stronger over time. Maybe there is an entirely new type of particle or field influencing expansion that we have not yet accounted for. Or the most unsettling possibility of all, our understanding of gravity itself, as described by Einstein, might need revision on the largest scales. This tension is more than a technical dispute. It is a crack in the foundation of modern cosmology. It signals that we are on the verge of another revolution, one that could reveal a universe far stranger and more dynamic than the one we think we inhabit. The very rate at which space itself stretches is telling us we have missed something monumental, and solving this crisis may require us to rewrite the rules of reality. While the Hubble tension pulls at the fabric of the cosmos, a more intimate search is unfolding right under our robotic feet. On the rusty, windswept plains of Mars, the Curiosity rover has been performing a slow, meticulous chemistry experiment for over a decade. In the heart of Gale Crater, a site believed to have once held a vast lake, the rover's drill has unearthed something revolutionary, not in a single eureka moment, but in a persistent, building whisper of evidence. It has detected a rich variety of organic molecules, the complex carbon-based building blocks essential for life as we know it. These are not proof of life itself, but they are the preserved ingredients, the chemical Legos scattered in the ancient mudstone, telling us that Mars once possessed the fundamental recipe. The real intrigue, however, breathes in the thin Martian air. Curiosity has also documented a mysterious, repeating pattern in the atmosphere, methane. On Earth, the vast majority of methane is produced by living organisms, from microbes to livestock. It is a gas that degrades quickly in sunlight, meaning any detection in the Martian air implies an active, recent source. Curiosity's data shows this methane doesn't just linger at a constant background level. It spikes dramatically and predictably during the Martian summer months. This seasonal pulse is a tantalizing clue. One explanation points to geology. Methane can be produced by water interacting with certain rocks like olivine in a process called serpentinization. It could also be released from ancient subsurface reservoirs, thawing slightly in the warmer season and venting through cracks in the ground. Yet the biological possibility hangs in the air, irresistible and profound. Could subsurface microbial communities, perhaps sheltered in briny aquifers deep below the freezing surface, be metabolizing and releasing this gas as a byproduct of their existence? The quest now is to distinguish between a living source and a geological one. Future missions, like the European Space Agency's Rosalind Franklin rover, will carry instruments designed to analyze the carbon isotopes within any methane they find. Life on Earth prefers to use the lighter carbon-12 isotope, leaving a distinct fingerprint in the methane it produces. If Martian methane shows that same preferential signature, it would be the strongest evidence yet that we are not alone. Mars has transformed from a dry, dead world into the solar system's most active crime scene. We have the building blocks in the ground and a mysterious gas breathing in seasonal cycles in the air. The rover is our detective, piecing together a story billions of years old, searching for the faint, fading signature of a neighbor that may have lived or might still live just beneath the dust. Even the strangest cosmic mysteries often find a home in natural explanations, but one star refuses to settle into a comfortable answer. Its official designation is KIC 8462852, but astronomers know it better as Boyajian star, or more dramatically, the star with the most bizarre light curve ever seen. Orbited by the Kepler Space Telescope, it should have blinked with the gentle, rhythmic dimming of a passing planet. Instead, its light pattern was pure chaos. The star's brightness would plummet by staggering amounts, sometimes over 20%, in irregular, jagged dips that lasted for days or weeks. These were not the clean, symmetrical shadows of a planet, but something vast, fragmented, and utterly opaque, blocking the light. The hunt for an explanation began with a frenzy of natural possibilities. Could it be a colossal swarm of comets, thousands of them, breaking apart and casting intricate shadows? Perhaps it was a vast cloud of interstellar dust drifting through the line of sight, or the lingering debris from a catastrophic planetary collision. Some even proposed the star itself was going through a strange, unstable phase, swallowing its own planets and belching out immense clouds of obscuring material. Each idea was explored, and each in turn encountered serious problems. A comet swarm large enough to cause such deep dimming seemed statistically implausible. Interstellar dust would likely affect neighboring stars, which it did not. The star itself appeared otherwise perfectly normal, a middle-aged main sequence star like our own sun, not a volatile youngster. As every conventional explanation strained under scrutiny, a far more speculative idea floated into the conversation, one born of sheer scale. Could these be the shadows of alien megastructures? The concept, first proposed by physicist Freeman Dyson, imagines a civilization so advanced it constructs a vast swarm of energy collecting panels or habitats around its star, a Dyson sphere, to harness nearly all of its power output. A partially built or fragmented swarm could produce exactly the kind of erratic, deep dimming observed. While this remains the least likely scenario, its enduring appeal is not as a serious claim but as a profound challenge. Boyajian's star forces us to confront the limits of our imagination. We are compelled to catalogue every possible natural phenomenon, to exhaust the entire known catalogue of cosmic events, because the alternative is to admit that something entirely new, perhaps even intelligently designed, might be out there. The star's true legacy is this lingering tension. It taught us that nature can produce signals so extreme they brush against the edges of science fiction, keeping a conversation alive that stretches from the rigorously possible to the thrillingly speculative, and reminding us that the universe has not yet run out of surprises. The chaotic light of Boyajian's star hints at cosmic construction, but in 2017 we witnessed a demolition of epic proportions, one we could both hear and see. For the first time in history, the ripples in spacetime predicted by Einstein, called gravitational waves, arrived not from colliding black holes but from a collision of two neutron stars. These are the impossibly dense cores of dead stars, each a city-sized sphere containing more mass than our Sun. As they spiraled inward over 100 million light-years away, their immense gravity churned the fabric of the universe, sending out a faint whisper that washed over Earth. The Laser Interferometer Gravitational Wave Observatory, or LIGO, detected this distinctive chirp, a rising frequency that told the story of a final, fatal dance. But this time, something else happened. Mere seconds after the gravitational wave signal ended, space-based telescopes caught a brilliant flash of gamma rays from the same patch of sky. The universe had sent us two different messengers from the same catastrophic event. Astronomers around the world swung into action, pointing every available telescope at that region. What they found was a kilonova, a fiery glow of radioactive debris expanding from the collision site. As they watched its light fade over days and weeks, their instruments detected the unmistakable spectral fingerprints of heavy elements being forged in the cosmic fire. This single event confirmed a long-held theory. The gold in your jewelry, the platinum in a catalytic converter, and much of the uranium on Earth were not born in the hearts of stars or in supernova explosions. They were created in the violent, neutron-rich maelstrom of colliding neutron stars, then blasted across the galaxy to become part of future planets and eventually us. This was the dawn of multi-messenger astronomy, a revolutionary new way of observing the cosmos. It is like being deaf and suddenly gaining hearing, allowing us to experience the universe in a symphony of information. By combining the gravitational wave signal, which tells us about the masses and dynamics of the objects, with the light from the explosion, which reveals their chemistry and speed, we get a complete picture no single observation could provide. This new window even offers a fresh way to tackle the Hubble tension, the crisis in measuring cosmic expansion. Gravitational waves give us a direct measure of the distance to the event, while the light from the kilonova reveals its velocity. Together, they provide an independent check on the universe's expansion rate, a new ruler built from the echoes of the most violent unions in the cosmos. Far beyond the chaotic collisions of distant stars, a subtle gravitational whisper is echoing through our own cosmic backyard. At the very fringe of our solar system, in the dark realm of the Kuiper belt, a population of icy objects is behaving strangely. Their orbits are not randomly scattered, but instead seem to be clustered together, as if herded by an unseen shepherd. Their elliptical paths are tilted at similar angles, and they swing out to their greatest distances in the same general direction of the sky. This peculiar alignment, discovered through painstaking computer modeling and observation, has led to a startling hypothesis. Something massive, perhaps 5 to 10 times the mass of Earth, is out there, its gravity sculpting the paths of these distant objects. Astronomers have named this hypothetical world Planet 9. It is not a direct observation, but a prediction written in the silent language of orbital mechanics. The search for this ghost planet is now one of the most compelling hunts in modern astronomy. Teams are using the world's most powerful telescopes, like Subaru in Hawaii, to scan vast swaths of the sky where calculations suggest it might be lurking. The challenge is immense. Planet 9, if it exists, would orbit about 20 times farther from the Sun than Neptune, making it incredibly faint and moving incredibly slowly against the background stars. A single orbit could take 10 to 20,000 years. Finding it is like searching for a single, dim streetlight in the pitch black of a continent-sized field, and you only have a few nights to look. Yet the potential reward is a complete rewrite of our solar system's history. How did such a large world end up so far out? One leading theory suggests it formed much closer to the Sun, alongside the other giant planets, before a gravitational tug-of-war with Jupiter or Saturn flung it out into a distant, eccentric orbit. Its discovery would not just add a new planet to our charts, it would reveal a violent, dynamic chapter in our system's youth that we never knew existed. It would prove that our familiar neighborhood of planets is the calm aftermath of a gravitational storm, and that a giant, silent member of our own family has been hiding in the darkness all along. While Planet 9 hides in the gravitational shadows, another discovery emerged from a visitor that came astonishingly close. The European Space Agency's Rosetta spacecraft spent 2 years orbiting a mountain of ice and dust known as Comet 67P, and its findings delivered one shock after another. The most profound was the detection of abundant molecular oxygen pouring from the comet's nucleus. This simple breath of air in the desolate vacuum of space was a staggering surprise. Oxygen is a fiercely reactive element, eager to bind with hydrogen to form water or with carbon to create carbon dioxide. In the violent, energetic environment of the young solar system, scientists were certain any free oxygen would have quickly locked itself away into other molecules billions of years ago. Finding it still pristine, trapped in the ancient ice of a comet, was like opening a prehistoric tomb and finding the air inside still fresh. This oxygen mystery forces a complete rewrite of the chemical story of our cosmic beginnings. The standard model of the protoplanetary disk, the swirling cloud of gas and dust that birthed our planets, could not explain how this oxygen survived. It suggests the comet formed in an extremely cold and gentle region of the disk, a place so frigid and quiet that oxygen molecules could freeze onto dust grains without reacting, preserving them in a deep freeze for over 4.5 billion years. Or it hints at a completely different chemical pathway happening right on the icy grains themselves, with high-energy particles from the young sun splitting water ice and releasing oxygen that became trapped. Comet 67P is a time capsule, and its contents are telling us the early solar system was far more chemically diverse and less destructive than we ever imagined. The very ingredients that eventually rained down on early Earth, potentially seeding our oceans and atmosphere, were more complex and richer than our models predicted. This oxygen is more than a gas, it is a message from our deepest past, challenging us to reimagine the calm, cold nursery where our world was born. The pristine oxygen of Comet 67P speaks of a gentle cosmic cradle, but some galactic nurseries seem to defy the very rules of construction. In the quiet constellation of Cetus, a ghostly galaxy named NGC 1052 DF2 drifts through space, a wispy collection of stars so sparse you could almost see straight through it. This type of galaxy is called an ultra-diffuse galaxy, but its true distinction is far more profound. When astronomers measured the motions of its bright star clusters, they found something that should not exist. The clusters were moving slowly, far too slowly for the amount of visible starlight the galaxy contained. According to the laws of gravity, a galaxy with that much visible mass should have a much stronger gravitational grip, whipping its star clusters around at higher speeds. The only explanation that fit the data was that this ghostly galaxy contains little to no dark matter. This single finding sent shockwaves through astrophysics. For decades, our entire model of galaxy formation has rested on a simple, powerful idea. Invisible dark matter forms first, creating vast gravitational wells in the early universe. Ordinary matter, the gas and dust that make stars and planets, then falls into these wells, clumping together to form the galaxies we see. Dark matter is not just a component, it is the essential cosmic scaffolding, the hidden framework upon which every galaxy is built. NGC 1052DF2 threatens to pull that framework apart. How do you build a galaxy without its foundation? One possibility is a violent past. Perhaps this diffuse galaxy was once a normal dwarf galaxy orbiting a much larger neighbor. A catastrophic gravitational encounter could have ripped away not only its stars but, in a precise cosmic robbery, stripped away its dark matter halo as well, leaving behind this ethereal skeleton of a galaxy. Another, more radical idea is that our understanding of gravity itself might need tweaking on galactic scales, a theory known as modified Newtonian dynamics, or MOND. This would mean the strange motions we see are not due to missing dark matter, but because gravity behaves differently when it is very weak. The discovery ignited fierce debate, with some teams reanalyzing the distance to the galaxy, arguing that if it were closer, its mass estimates would change. Yet subsequent studies of similar galaxies have reinforced the original finding. This ghostly galaxy and others like it are not flukes, they appear to be a genuine class of cosmic objects. Their existence does not necessarily disprove dark matter, but it does prove that the universe has more than one way to build a galaxy. It forces us to confront the messy, violent, and still mysterious processes that shape cosmic structures, reminding us that even our most fundamental ideas must leave room for the universe's bewildering creativity. The ghostly galaxies missing their dark matter challenge our cosmic blueprints, but another world in our own neighborhood is revealing a surprisingly vibrant interior. For decades, Venus was seen as a geologically dead world, its surface frozen in time under a crushing, toxic atmosphere. That quiet assumption erupted into doubt in 2023, when scientists staring at decades-old data saw something move. They were re-examining radar maps from NASA Magellan mission, which mapped Venus in the early 1990s. By comparing images of the same volcanic vent region taken 8 months apart, they spotted a dramatic change. A vent near the massive volcano Mont Mons had transformed. In the first image, it appeared as a circular opening. 8 months later, the second radar pass showed the same vent had nearly doubled in size and morphed into a ragged kidney bean shape. The surrounding terrain was also brighter in the radar return, suggesting fresh, rough lava flows had spilled out and cooled. This was not ancient history. This was evidence of change, of geological activity happening within a human timescale. The implication is staggering. Venus is volcanically active right now. This single observation rewrites the story of our sister planet. We now know it is not a static, fossilized landscape, but a world with a beating, molten heart. This forces a profound rethink of planetary evolution. Earth and Venus are nearly twins in size and composition, yet they diverged onto wildly different paths. We have plate tectonics, a global recycling system that regulates our climate and fuels our magnetic field. Venus appears to have a stagnant lid, a single, unbroken crust. But without plate movement, how does the immense heat from its interior escape? The answer seems to be episodic, catastrophic resurfacing. Venus may experience planet-wide volcanic paroxysms every few 100 million years, where the entire crust cracks and melts in a global inferno, burying the old world under miles of fresh lava. The discovery of current activity suggests we might be living in a quieter period between these apocalyptic events, but a period where the fires still simmer and occasionally break through. This changes everything about Venus's potential past. A geologically active world is a world that could have recycled chemicals, released gases, and perhaps even regulated its temperature. It opens the door to a tantalizing, though still speculative, possibility. If Venus had liquid water on its surface in the distant past, as some climate models suggest, Its volcanoes could have played a role in creating and sustaining environments where life might have gained a foothold before the runaway greenhouse effect boiled it all away. Our hellish neighbor is no longer a dead end. It is a dynamic world, a cautionary tale of climate catastrophe, and a living laboratory showing us one extreme path a rocky planet can take. The volcanic fires of Venus reveal a dynamic world, but the true architects of cosmic chaos may be found in the silent, random flicker of a distant sun. A star designated HD 139139 presented astronomers with a puzzle so perplexing it earned the nickname the Random Transitor. Data from the Kepler Space Telescope showed this otherwise ordinary star dimming not with the steady rhythm of an orbiting planet, but in a chaotic, unpredictable stutter. Over an 80-day period, it experienced dozens of these brief dips in brightness, each resembling the shadow of a planet crossing the star's face. The maddening part was the complete lack of a pattern. If these were planets, their orbits made no sense. They seemed to cross at random intervals, sometimes in quick succession, other times with long gaps of silence. It was as if someone was sporadically throwing rocks of different sizes between the star and our telescopes. Natural explanations were strained to the limit. A swarm of comets or asteroids could cause irregular dimming, but to produce so many distinct, clean dips without any accompanying dust signature seemed unlikely. The possibility of a vast, fragmented ring system around a planet was proposed, but even that would tend to create some repeating structure as the planet itself orbited. The randomness itself became the central clue, pointing toward something intrinsically disordered happening in that system. This is where the mystery pushes science to its creative limits. Astronomers began considering phenomena we have never directly observed. Could it be the aftermath of a colossal planetary collision, with moon-sized chunks of debris now on chaotic, intersecting orbits around the star? Perhaps it is the signature of intense stellar activity, with enormous magnetic loops or star spots creating temporary, deep shadows as they rotate in and out of view. Or, in the most speculative realm, could it be evidence of exomoons being torn from their parent planets, creating a temporary cloud of eclipsing material? The Random Transitor stands as a monument to cosmic confusion. Its value is not in providing an easy answer, but in demonstrating how much we still have to learn about the intricate dances within other solar systems. It forces astronomers to invent new categories of events, to imagine processes of planetary demolition and stellar tantrums on scales we can barely comprehend. In the silent, digital data from a telescope, we found a star that seems to be blinking in a code we cannot yet crack. A reminder that for every elegant rule the universe establishes, it enjoys creating a beautiful, bewildering exception. Chaos in distant star systems reveals the universe's capacity for surprise, but one image managed to transform our most profound cosmic theory from abstract math into visceral reality. In April 2019, a global collaboration of radio telescopes, synchronized to act as a single Earth-sized instrument called the Event Horizon Telescope, unveiled a picture that stopped the scientific world in its tracks. It was a fiery, asymmetric ring of light encircling a central region of profound darkness, the shadow of the supermassive black hole at the heart of the galaxy Messier 87. This was not an artist's impression or a simulation. It was a direct observation, a photograph of the point of no return. The dark void at the image center is the black hole's shadow, a region where gravity is so overpowering that not even light can escape. The bright ring surrounding it is the accretion disk, superheated gas and dust spiraling inward at nearly the speed of light, its light bent into a perfect circle by the black hole's immense gravitational lens. The ring's lopsided brightness, brighter on one side, is a direct prediction of Einstein's theory of general relativity. It shows the side of the disk that is rotating toward us, its light boosted by relativistic effects, while the other side, spinning away, appears dimmer. This single, grainy orange donut was a monumental confirmation. For decades, black holes existed as mathematical necessities, objects so logical within Einstein's framework that they had to be real, yet they remained theoretical phantoms. The M87 image changed that forever. It provided the first direct visual evidence that these cosmic monsters are not just ideas, but actual physical structures in space, with sizes and shapes that match our most daring predictions. But this achievement is more than a trophy, it is a powerful new tool. By continuing to observe this shadow and the one at our own galaxy's center, Sagittarius A star, scientists can now perform precision tests of gravity in its most extreme regime. Does the shadow's size match exactly what general relativity predicts for a black hole of that mass? Could tiny deviations reveal where Einstein's theory might begin to break down, hinting at a deeper, more complete law of physics? The Event Horizon Telescope did not just take a picture, it opened a new window. It allows us to witness the violent ballet of matter at the edge of existence, and to interrogate the fundamental rules that govern reality itself, all from the shadow cast by a gravitational abyss 55 million light-years away. That shadow is a monument to gravity's ultimate power, but on a map of the universe's first light, there is an emptiness that suggests a power from beyond. Etched into the cosmic microwave background, the afterglow of the Big Bang is a feature so strange it has simply been named the cold spot. It is a vast circular region, nearly 1 billion light-years across, where the temperature of the ancient radiation is significantly colder than the surrounding sky. This isn't a tiny fluctuation, it is a cosmic bruise, a giant, frigid anomaly that our standard models struggle to explain. At first, astronomers thought it might be a statistical fluke, a rare but possible random variation in the primordial soup. Yet as measurements improved, the probability of it being just a random accident dwindled to less than 1 in 200. This cold spot is real, and it demands a more dramatic story. One compelling theory involves a cosmic defect called a texture. In the frenzied energy fields of the early universe, as fundamental forces were splitting apart, knots of energy might have frozen into the fabric of spacetime. If our observable universe passed through one of these knots, it would have left a distinct imprint, a cold spot in the cosmic background, like a phantom scar from the universe's violent birth. But there is an even more staggering possibility. This colossal chill could be evidence of a collision, a crash between our infant universe and another, entirely separate bubble of reality during the period of hyper-expansion called inflation. According to this mind-bending idea, our entire cosmos is just one bubble in a frothing multiverse. If a neighboring bubble brushed against ours in those first fleeting moments, the energy of that impact could have drained away, leaving behind a vast, cooler region in its wake, a cosmic fingerprint from another universe. This makes the cold spot more than an anomaly, it is a potential window. If it is a collision scar, then we are not just mapping the boundaries of our universe, we are glimpsing what lies beyond its edges, seeing the imprint of a reality that operates under entirely different physical laws. It remains one of the most tantalizing and persistent cracks in our standard model of cosmology, a quiet, cold whisper on the oldest map we have, suggesting that our story may be just one chapter in a library of universes we are only beginning to imagine. The cosmic cold spot hints at collisions on a universal scale, but a single star in our own galactic neighborhood recently staged a dramatic and deeply personal preview of its own violent end. In late 2019, the shoulder of the constellation Orion began to falter. Betelgeuse, one of the brightest and most recognizable red supergiant stars in our sky, started to dim. This was not a subtle flicker. By February 2020, its light had dropped to about 35% of its normal brilliance, a change visible even to the naked eye. Astronomers watched with a mixture of awe and apprehension. Was this the final act? Was Betelgeuse, a star known to be in the final millennia of its life, about to go supernova? The world held its breath, waiting for a cosmic explosion that would outshine the full moon, but the explosion never came. Instead, the star gradually returned to its former brightness over the following months, leaving behind a profound mystery. What had just happened? Telescopes around the world and in space, including the Hubble, turned their gaze to solve it. The answer was not a pre-supernova collapse, but something almost as spectacular. The star had belched. Detailed analysis revealed that Betelgeuse had ejected a colossal cloud of superheated plasma from its surface. As this material moved away, it cooled into a vast shroud of fine dust grains, literally forming a cosmic soot cloud that drifted between the star and our line of sight, dimming its light. This was a monumental stellar event, a chance to watch the death throes of a giant star in real time. For a star like Betelgeuse, which is over 10 times more massive than our Sun, its final years are a turbulent, unstable dance. It pulses and heaves, shedding its outer layers in great convulsions before its core finally collapses. The Great Dimming was a front-row seat to one of those convulsions. We learned that these dust ejections are not smooth, gentle processes. They are violent, localized eruptions, likely driven by massive convective cells like boiling bubbles the size of a solar system rising from the star's churning interior and throwing material clear off the surface. This single event transformed Betelgeuse from a distant point of light into a detailed laboratory. It gave us unprecedented data on how these stars lose mass, how they seed their surroundings with the heavy elements that will form future planets, and what the specific warning signs might be in the years or centuries before they finally explode. When Betelgeuse does go supernova, and it will, we are now far better prepared to understand every step of that breathtaking finale. Betelgeuse's Great Dimming was a natural stellar event, but sometimes the universe sends us a mystery that turns out to be a piece of our own history. In September 2020, astronomers spotted a faint object on a path that would bring it extraordinarily close to Earth. Initially catalogued as a small near-Earth asteroid and named 2020 SO, its orbit was peculiar. It moved too slowly, and its path around the Sun was almost identical to our own planet's, a telltale sign that raised immediate suspicion. This was not a random rock from the asteroid belt. Further analysis of its motion under the subtle pressure of sunlight revealed its true nature. The object had an abnormally low density, a high area-to-mass ratio, meaning sunlight could push it around like a hollow shell. The trajectory data told the final story. By tracing its path backward through decades, astronomers found a perfect match. 2020 SO was not an asteroid at all. It was the spent Centaur rocket booster from NASA, a Surveyor 2 lunar lander mission launched in September 1966. After helping push the spacecraft toward the moon, this piece of 20th century engineering drifted silently through space for 54 years, completing endless loops around the Sun, until Earth's gravity finally reached out and gently captured it into a temporary orbit around its home planet. For several months, this ghost from the early space age became a tiny, wobbling moon, a human-made artifact returning as a cosmic curiosity. This discovery highlights a fascinating new reality in near-Earth astronomy. Our celestial neighborhood is no longer just a realm of natural objects. It is becoming cluttered with the relics of our own exploration, discarded rocket stages, dead satellites, and fragments from collisions. These artificial asteroids now mingle with the real ones, and telling them apart is a critical, growing challenge. As we launch more missions, the lines will blur further. This is where the next great leap in cosmic surveillance comes in. The Vera C. Rubin Observatory, currently being built in Chile, will soon begin the most comprehensive astronomical survey ever attempted. Every few nights, its immense mirror and giant camera will capture the entire available sky, not just once, but over and over for a decade. It will detect billions of objects, from distant galaxies to faint asteroids whizzing past Earth. Its primary mission is to map the dark universe and find potentially hazardous asteroids. but it will also become an unparalleled tracker of our own space junk. By spotting these artificial objects repeatedly and calculating their orbits with precision, the observatory will help us maintain a cosmic catalogue that distinguishes between a natural near miss and a piece of our own past swinging back for a visit. The story of 2020 SO is a whimsical reminder that our reach into the cosmos has lasting echoes. We are not just observers of the solar system anymore, we are active participants, leaving signatures that future astronomers, human or otherwise, might one day puzzle over as they scan the skies. The ghostly artifacts of our own making drift close to home, but on the largest scales imaginable, the entire cosmos seems to be caught in a mysterious current. Hundreds of galaxy clusters, each containing thousands of galaxies, are not moving randomly. Instead, they appear to be streaming together in a coordinated rush toward a specific point in the sky, a phenomenon astronomers call the dark flow. This isn't the general expansion of the universe which pulls galaxies apart. This is a peculiar additional motion, as if these immense structures are being tugged by something titanic lying far beyond the edge of everything we can see. The measurements taken by studying the cosmic microwave background in relation to these clusters suggest they are racing at speeds of over 2 million miles per hour in the same direction. The sheer scale of this coordinated motion is what defies explanation within our standard model of cosmology. Gravity from any known structure within our observable universe, like a supercluster of galaxies, is simply not strong enough to create this kind of coherent pull on such vast distances. The source of the tug must be inconceivably massive, and crucially, it must lie outside our cosmic horizon. This is where the implications become truly staggering. One leading, though highly controversial, theory is that the dark flow is the gravitational fingerprint of another universe. In a multiverse scenario where our cosmos is one bubble in a frothing sea of space-time, the immense mass of a neighboring bubble universe could be exerting a pull on our own, drawing everything toward it like a cosmic magnet. Another possibility is that it's evidence of a region of space-time with radically different properties, a remnant scar from the universe's violent inflationary birth that warps the fabric of reality on a scale we can barely comprehend. Not all scientists accept the dark flow data, with some arguing it could be a subtle systematic error in the incredibly difficult measurements. Yet if it is real, it means the map of the universe we've painstakingly assembled is incomplete. There are forces at work from realms we cannot observe, pulling the strings of the largest structures in existence. It suggests our entire cosmic neighborhood, hundreds of millions of light years across, is sailing on a hidden river, flowing toward a destination we cannot yet see. The dark flow hints at unseen forces shaping the cosmos, but the James Webb Space Telescope has now looked directly into the dawn of time and found a structure that simply should not be there. Its designation is a string of numbers and letters, CEERS-93316, but its story is one of pure cosmic defiance. This faint smudge of light, captured by Webb's penetrating infrared eye, is the image of a galaxy as it existed when the universe was only 250 million years old. That is an almost incomprehensibly short time after the Big Bang, a period when the cosmos was still a murky, opaque soup of cooling gas. Yet this galaxy is not a faint infant seed. Analysis of its light suggests it is already massive, containing billions of stars, and it appears mature, its stars having already formed and evolved for many millions of years. This presents a glaring, fundamental problem for our theories of cosmic evolution. According to our best models, there simply was not enough time after the Big Bang for gravity to pull together such vast clouds of gas, for those clouds to fragment into the first generation of stars, for those stars to live, die in supernova, and then for a second generation of stars to form from the enriched debris, all culminating in a settled, massive galaxy. A process should have taken at least 500 million to a billion years. CEERS 93316 did it in half that time or less. It is like finding a fully grown oak tree in a forest you planted only a year ago. The existence of this galaxy and others like it that Webb is now finding forces a radical rethink of the universe's earliest chapters. Perhaps the first stars formed not in the slow, gradual way we envisioned, but in sudden, explosive bursts within incredibly dense pockets of primordial gas. Maybe dark matter, the invisible scaffolding of the cosmos, clumped together far more quickly and efficiently than our simulations predicted, creating deep gravitational wells that funneled ordinary matter into ready-made stellar factories at breakneck speed. Or it could be that our entire timeline for the cosmic dawn is off, and the universe became transparent to light earlier than we thought, giving structures a head start. Each of these possibilities shakes the foundations of modern cosmology. These impossible galaxies are not just ancient curiosities, they are urgent clues written in starlight. They tell us that the infancy of the universe was a period of extreme and accelerated physics, a frenzied construction phase where the rules were different and the pace was blistering. To understand them is to understand how the universe went from a formless fireball to a structured, star-filled cosmos in what amounts to a cosmic heartbeat. Those ancient, impossible galaxies are rewriting the dawn of time, but a discovery in our own solar system has rewritten the very definition of a living world. Far out by Saturn, a small, icy moon named Enceladus gleams with a purity that masks a stunning secret. For years, astronomers saw it as a frozen marble, a mere 400 miles across, reflecting almost all the sunlight that touches it. That pristine image shattered when the Cassini spacecraft arrived. Its cameras revealed a landscape of shocking youth with few impact craters and a series of deep, parallel cracks near the South Pole nicknamed the Tiger Stripes. But the real revelation came not from the surface but from what was shooting off of it. Cassini witnessed colossal geysers, towering plumes of water vapor and ice crystals erupting from those tiger stripe fractures, jetting hundreds of miles into space. This was not a dead ball of ice, it was an active world crying out into the vacuum. The plumes were a gift, a sample delivered straight from the moon's interior into Cassini's waiting instruments. As the spacecraft flew through these icy jets, its sensors tasted their contents. They found simple organic molecules, the carbon-based building blocks for life. They detected salts like sodium chloride, ordinary table salt, and sodium carbonate, similar to baking soda. Most importantly, they found silica nanograins, tiny particles that scientists concluded could only form in hot water, at temperatures of at least 190 degrees Fahrenheit, interacting with a rocky seabed. The picture that emerged was breathtaking. Enceladus is not just venting steam from a shallow pocket of meltwater. It possesses a global, salty ocean, trapped between its icy crust and a warm, rocky core. At the seafloor, hydrothermal vents, much like those that teem with life in Earth's deepest oceans, are likely spewing mineral-rich, superheated water into the dark abyss. This creates the perfect recipe for life as we know it: liquid water, a source of chemical energy from the rocks and the essential organic ingredients. Every element needed for a habitable environment is there, mixing in a sunless sea beneath the ice. This transforms Enceladus from a curiosity into arguably the most promising place to search for life beyond Earth. We do not need to drill through miles of ice to find it. The moon is doing the work for us, launching potential biosignatures or even frozen microbial hitchhikers directly into space. A future mission could simply fly through a plume, collect the icy particles, and analyze them for the complex chemistry of life. In the dark, under an icy shell, a tiny moon orbits a ringed giant, holding an ocean that may whisper an answer to our oldest question. Deep within our own galaxy, a monster breathes, 28,000 light-years away, in the constellation Aquila, a binary star system named GRS 1915+105, hosts a stellar mass black hole locked in a deadly dance with a companion star. This black hole is not quiet. As it pulls gas from its neighbor into a swirling, superheated disk, the system erupts as a microquasar, a miniature version of the violent quasars seen in distant galactic cores. But this particular monster has a rhythm. For decades, X-ray telescopes have detected a strange, repeating pulse in its emissions, a signal that rises and falls with a quasi-periodic oscillation. Astronomers have likened it to a heartbeat. This is not the steady ticking of a clock, but a complex, variable throb emanating from the innermost region of the accretion disk, mere miles from the black hole's event horizon itself. The heartbeat source is a delicate, violent balance. As immense amounts of matter spiral inward, they pile up at the inner edge of the disk, heating to millions of degrees and glowing fiercely in X-rays. This buildup creates pressure until it triggers an eruption, a release of energy and material that drains the inner disk. Then, the cycle begins again as fresh gas flows in to refill the region, building toward the next pulse. This rhythmic flicker is a direct probe into the most extreme gravitational environment we can observe. By studying the timing, the energy, and the structure of this heartbeat, scientists can test Einstein's theory of general relativity in a regime of unimaginable gravity and spin. The oscillations act like a natural sonogram, revealing details about the space-time curvature right at the precipice of the abyss. They tell us about the black hole's spin, the dynamics of magnetized plasma moving at near light speed, and how energy can be extracted from the very rotation of space-time itself, a process predicted by physicist Roger Penrose. No laboratory on Earth could ever recreate these conditions. We cannot make a black hole, nor can we spin plasma to relativistic speeds in a controlled way. But nature has provided this precise, rhythmic laboratory in the depths of space. Each pulse from GRS 1915 plus 105 is a data point, a message from the edge of the impossible, helping us write the physics textbook for realms where gravity is the only law that matters. Even the rhythmic heartbeat of a black hole can be silenced by a far more violent encounter. In a distant galaxy, the Hubble Space Telescope captured a scene of cosmic abandonment so strange it seemed to defy logic. Streaking across the void was a supermassive black hole, a gravitational titan weighing as much as 20 million suns, and it was not at the center of anything. It was fleeing. This cosmic fugitive was racing away from its host galaxy at over 5 million miles per hour, so fast it could travel from Earth to the Moon in under 15 minutes. In its wake, it left not destruction, but a brilliant, narrow trail of newborn stars stretching over 200,000 light-years, twice the diameter of our Milky Way. This was no random path of devastation. The black hole was moving so rapidly it was plowing into the thin gas floating in intergalactic space, compressing and shocking that material in front of it. Instead of being consumed, that gas was being herded, squeezed, and triggered into collapsing under its own gravity, igniting a continuous chain of stellar nurseries. The image was breathtaking, a river of blue-white infant stars flowing through the darkness, with the invisible engine of their creation speeding ahead at the tip. How does a galaxy lose its central heart? The answer lies in gravitational chaos. Astronomers believe this black hole was once part of a triple system at the galaxy's core, the result of two smaller galaxies merging in the past. When a third galaxy merged, it brought its own supermassive black hole into the mix, creating a volatile dance of three immense masses. In this gravitational pinball, one of the black holes likely received a tremendous slingshot effect from the other two, flung clear out of the galactic center entirely. This observation is not just a spectacular oddity, it is direct visual proof of a long-theorized but never-seen process. It reveals that the lives of galaxies are far more violent and dynamic than their serene appearances suggest. Mergers and collisions are not tidy events. They can literally catapult the most massive objects in the universe into the intergalactic wilderness. This runaway black hole and its star-forming wake show us that the seeds of creation can be sown by the most powerful forces of ejection, forever changing our view of how stars can be born in the lonely voids between galaxies. This runaway giant is a testament to cosmic violence, but from the deepest quiet of our solar system, another giant is approaching with a message from the dawn of time. Designated C 2014 UN 271, but known as Comet Bernardinelli-Bernstein, this is no ordinary icy visitor. It is a behemoth, a mountain of ice and dust estimated to be a staggering 85 miles across. To put that in perspective, its nucleus alone is larger than the state of Rhode Island, making it the single largest comet humanity has ever identified. It was discovered not by its bright tail, but as a faint, slow-moving speck in data from the Dark Energy Survey, a project designed to map distant galaxies, not hunt for local ice. Its detection was a cosmic coincidence of the best kind. This comet is a messenger from the farthest frontier, the Oort cloud. This is a theoretical shell of icy debris that surrounds our solar system like a distant, frigid halo, beginning nearly 1 trillion miles from the Sun and extending perhaps halfway to the next star. Comet Bernardinelli-Bernstein has spent millions, maybe even billions, of years drifting in this deep freeze, a pristine relic from the era when the planets were still forming. Now, its long, elliptical orbit is bringing it inward on a million-year journey toward the warmth of the inner solar system. There is absolutely no danger. Its closest approach to the Sun will still be beyond Saturn's orbit. Its immense distance is actually our greatest opportunity, because it will not plunge too close to the Sun. Its surface will not be violently cooked and transformed by solar heat. As it slowly warms, it will develop a coma and tail, but its nucleus will remain relatively undisturbed. This gives astronomers a chance to study a sample of the solar system's original building blocks in their most unaltered state. Using telescopes like the James Webb, scientists will analyze the light reflected from its coma, looking for the chemical fingerprints of ancient ices and complex organic molecules that have been locked away since the birth of our planetary family. This megacomet is a time capsule on a grand scale. Its composition is a direct record of the conditions in the outer solar nebula over 4.5 billion years ago. By deciphering its chemistry, we are not just studying a comet, we are reading the recipe book for the outer planets, for the icy moons, and for the water and organic material that may have been delivered to the early Earth. This distant, slow-moving giant carries within its frozen heart the very ingredients and the untold story of our cosmic origins. The monstrous black holes from the universe's infancy demanded a growth mechanism, and now we may have caught them in the act. The James Webb Space Telescope has peered back over 12 billion years and captured a stunning sight, not one, but two brilliant quasars blazing side by side in the heart of a pair of colliding galaxies. A quasar is the intensely luminous core of a distant galaxy, powered by a supermassive black hole feasting on a torrent of gas. To find two of these cosmic beacons so close together, and at such an early cosmic epoch, is like finding twin lighthouses on a primordial shore, signaling a monumental event. This double quasar system is a snapshot of a critical moment, a direct view of the very process theorists needed to explain how black holes grew so big so fast. Here we see two galaxies, each with its own central black hole, drawn together by gravity. As the galaxies swirl and merge, their black holes begin a deadly dance, orbiting one another in an ever-tightening spiral. This discovery provides the first clear observational evidence for a fundamental prediction, that the giant black holes we see in the young universe did not grow in isolation. They grew by merging, by cannibalizing each other in violent galactic collisions. Imagine two massive whirlpools in a cosmic ocean, slowly circling until they combine into a single, more powerful vortex. Each merger instantly doubles the mass of the resulting black hole, providing a shortcut to building a billion solar mass monster in a fraction of the time it would take by slowly sucking in gas alone. This double quasar is the missing link, the direct evidence that the impossible early giants from Webb's earlier observations could have been forged in the fires of frequent, frantic mergers. It suggests the dawn of the cosmos was not a serene period of gentle growth, but a chaotic, clanging construction site where galaxies and their dark hearts constantly smashed together, building the foundations of the modern universe through a relentless series of cosmic crashes. For decades, our cosmic inventory had a glaring, embarrassing hole. We could account for all the dark matter and dark energy, but when it came to the ordinary matter that makes up you, me, and every star and planet, our math was off by a staggering 50%. This was the missing baryon problem. Baryons are the particles of normal stuff, protons and neutrons, the building blocks of atoms. Based on the pristine conditions of the early universe, measured in the cosmic microwave background, we knew exactly how much of this ordinary matter should exist today. Yet when astronomers added up all the stars, galaxies, and visible gas clouds, they came up short. Half the universe's ordinary mass was simply gone, hiding somewhere in the vast cosmic dark. The solution was as elegant as it was difficult to see. Theorists long suspected the missing matter was floating in the form of an incredibly diffuse, superheated gas strung along the filaments of the cosmic web. This is the large-scale structure of the universe, a network of dark matter upon which ordinary matter condenses into galaxies, with tendrils of gas stretching between them in million light-year threads. The gas in these filaments is so thin, only a few atoms per cubic meter, and so hot, at millions of degrees, that it doesn't emit the kind of light our telescopes can easily catch. It is the universe's faint, ghostly atmosphere. To find it, we needed a cosmic flashlight, and nature provided one in the most energetic form imaginable: fast radio bursts. As these brilliant millisecond flashes travel billions of light years to reach us, their radio waves pass through every bit of material between their source and Earth. When the waves hit that hot, diffuse intergalactic gas, they slow down slightly, and different frequencies are delayed by different amounts. By measuring this subtle dispersion in the signal of many FRBs coming from many different distances, astronomers can essentially weigh the fog. They can calculate how much ionized gas the burst passed through on its long journey. The results were a triumph of indirect detection. By analyzing the accumulated signals from numerous FRBs, scientists confirmed that a massive reservoir of that superheated, ordinary gas does indeed fill the spaces between galaxies, exactly tracing the predicted filaments of the cosmic web. This wasn't a small find. It accounted for the bulk of the missing 50%. The lost matter wasn't truly lost. It was hiding in plain sight, woven into the very fabric of the universe, too faint to see but too substantial to ignore. With this discovery, we finally balanced the cosmic books for ordinary matter. It closed a major chapter in cosmology, proving that our map of the universe, while still filled with dark mysteries, at least now correctly charts all the visible stuff. The universe had hidden its atoms in the last place we thought to look, in the scorching, empty-seeming voids between everything. That ghostly gas between galaxies is just one form of invisible cosmic matter, but another has traveled the universe completely unhindered since its violent birth. In September 2017, a single, nearly massless particle struck a sensor buried deep within the Antarctic ice. This was no ordinary impact. It was a high-energy neutrino, often called a ghost particle, and it carried a specific, traceable energy signature. For the first time, the IceCube Neutrino Observatory was able to pinpoint not just its arrival, but the precise direction it came from. Astronomers swung their telescopes to that patch of sky and found a brilliant, blazing object 4 billion light-years away. It was a blazar known as TXS 0506+056, a galaxy with a supermassive black hole at its core, shooting a jet of radiation and particles directly at Earth. This was a landmark moment in cosmic detective work. Neutrinos are the universe's ultimate ghosts. They are produced in nuclear reactions from the sun's core to the most cataclysmic explosions, and they have almost no mass and no electric charge. This means they barely interact with normal matter, flying straight through planets and stars as if they were not even there. Trillions pass through your body every second without a trace. Their ghostly nature is also their power, for they travel in perfectly straight lines from their source, unaffected by magnetic fields that bend other charged particles. Finding one is incredibly difficult, requiring massive detectors like IceCube, which uses a cubic kilometer of pristine Antarctic ice as its sensor. When that one high-energy neutrino arrived with a cosmic return address, it was the final piece of a multi-messenger puzzle. The Blazar's jet, powered by its central black hole, is a natural particle accelerator of almost unimaginable power. Protons and other particles are whipped to near light speed within it, and when they collide, they create a cascade of secondary particles, including both gamma rays and these high-energy neutrinos. For decades, we knew such accelerators must exist, but we could never definitively prove which cosmic objects were responsible. This single ghost particle changed that. By linking it directly to the blazar, which was also erupting in gamma rays at the same time, scientists had their first concrete evidence. They could finally say with certainty that the jets from supermassive black holes are factories for these elusive cosmic ghosts. This opens an entirely new window onto the most violent engines in the universe. We can now use neutrinos as direct probes, as messengers that bring us untouched information from deep inside these chaotic, magnetic maelstroms, realms so extreme that even light cannot faithfully escape their complexity. The ghost has pointed a finger back at its monstrous creator, giving us a new way to see the invisible engines shaping the cosmos. From the ghostly touch of a neutrino to the monumental crash of galaxies, we have traced cosmic mysteries across the universe. Yet one of the most profound clues to a deeper reality was found not in deep space, but in a circular racetrack buried under the plains of Illinois. At the Fermi National Accelerator Laboratory, scientists have been meticulously studying a fundamental particle called the muon. Think of it as a heavy, unstable cousin of the electron, and like a tiny spinning magnet, it possesses a property known as its magnetic moment, essentially how strongly it wobbles in a magnetic field. For decades, the standard model of particle physics, our rulebook for the subatomic world, has predicted exactly how this wobble should behave. The experiment, named muon G-2, was designed to measure this wobble with unprecedented precision. The results, however, did not match the prediction. The muon's wobble is ever so slightly stronger than the standard model says it should be. This tiny discrepancy is what physicists call an anomaly, and it is sending shockwaves through the foundations of modern physics. It means something is missing from our equations, an invisible influence nudging the muon in its magnetic dance. The most thrilling possibility is that this nudge comes from particles or forces that are entirely new to science, components of a hidden universe that permeates our own. These could be the very same particles that make up the dark matter holding galaxies together, or carriers of a fifth fundamental force of nature beyond gravity and electromagnetism. This means the anomaly in a lab in Illinois is not an isolated curiosity. It is a direct, measurable signal that the cosmos is governed by laws we have not yet written. The same hidden physics that tweaks a muon spin in an accelerator could be sculpting the vast cosmic web, accelerating the universe's expansion, or even explaining the impossible brightness of early galaxies. We are no longer just looking out at cosmic mysteries from a distance. We have built a machine that has felt the whisper of those mysteries, a whisper carried on the spin of a fleeting particle. The muon's tiny wobble is a crack in reality's door, and through it we are glimpsing the silhouette of an entire new layer of existence, one that could connect every strange discovery from the beginning of time to the laboratory floor. From the ghostly spin of a muon to the impossible light of ancient galaxies, these 30 discoveries are not isolated curiosities. They are a chorus of whispers from the cosmos, each one chipping away at the walls of our ignorance. We have learned that water hides in sunlit lunar soil, that our solar system may host a hidden giant, and that the very rate of the universe's expansion is a point of fierce debate. We have tasted the breath of comets, felt the heartbeat of black holes, and seen stars vanish behind shadows we cannot yet name. Every mystery solved seems to unlock 2 more, revealing a cosmos far stranger, more dynamic, and more ingeniously weird than the orderly universe we once believed in. The common thread running through them all is not a single answer but a profound shift in perspective. We are not passive observers in a static, clockwork universe. We are participants in an ongoing, violent, and breathtakingly creative story, one written in the language of gravitational waves, organic molecules, and phantom particles. This is the true gift of these discoveries. They do not just give us new facts, they give us new questions, expanding the frontier of the unknown faster than we can map it. So let this not be an end but an invitation. The next time you look up at the night sky, remember that you are not looking at a static canopy of lights. You are looking at a living, breathing, and deeply mysterious cosmos where impossible black holes are born, where life might drift in alien clouds, and where the very fabric of reality is being questioned. The journey of discovery is just beginning. Stay curious, follow the science, and keep looking up. The universe still has so much left to tell us.